In this video, we discuss conduction in detail. So, what is conduction? We all know that it is a transfer of heat through a solid without the actual movement of the particles of the medium. Now, I consider a metallic rod and 4 thermometers are kept like this, and when I start heating from this end will be the hot end, and from here, as per the process of conduction, the molecules will be gaining thermal energy and starts vibrating, and through that vibration the next molecule, the neighboring molecules are also getting that hit from the vibrating molecules, and that forced vibrations will be carrying on through this, and energy is passing through this conductor. Now you can see, as the heating is going on, the thermometer here will be showing a little bit of rise of temperature, but other thermometers will be in low position itself. And as I continue to heat for a long time, I can see that the first thermometer reads up to the maximum here, second thermometer here, third thermometer, and the last one here. That means all the 4 thermometers will be reading a constant value, but depending upon the distance from the hot end, the thermometer reading value will be getting lower and lower. If I continue to heat again, what you can observe is that the thermometer reading is not going to change. Each thermometer will be showing the same temperature reading. Now at this stage we say the system has reached what you call thermal steady state. Steady state. Now when the steady state is reached, what is happening here is that the rate of flow of heat through any section of the conductor remain constant. If you take a small section here or here, you can see that the rate of flow of heat remain a constant, or this rate of flow of heat is called heat energy flowing per time, and also called heat current. Heat current, we can see. Rate of flow is also known as what? Heat current. Now, at this particular state, we can write an equation for the rate of flow of heat or the heat current by assuming a section of the conductor. I consider a section of this conductor of thickness x, and the first phase reading of temperature is theta 1 and the other end reading is theta 2. So obviously we can have theta 1 is greater than theta 2. It's from the figure because the temperature is decreasing from the hot end to the cold end. Now at this stage, what we can observe is that the rate of flow of heat Q by T is found to be directly proportional to the area of cross section of the conductor, and rate of flow of heat is found to be directly proportional to theta 1 minus theta 2, the difference in temperature divided by thickness, and this is called temperature gradient. We have seen another gradient, that was velocity gradient and viscosity. Now we are having a temperature gradient, that is a decrease of temperature along the conduction path with respect to the thickness. Okay? Therefore, we can write Q by T equal to K into A into theta 1 minus theta 2 by x. A formula like this can be obtained from the observation, and where K is called thermal conductivity of the material of the body. Thermal conductivity. It depends on the nature of the material you are considering. Okay, it's a new quantity. Now the same formula we can discuss in a, what do you call it, calculus way, that is by applying the rate of change, where I can write this as dq by dt, that is equal to K into A into d theta by dx. This is the differential form of what we call the rate of flow. And here you can have a negative sign because the heat energy is decreasing, or the temperature is decreasing along the direction of flow of heat. That is why there is a negative sign. And this equation is called Fourier's law. Fourier's law in conduction. Okay? So, these two are the factors on which the rate of flow depends, and from there you can come up to this. Alright? Now, two more points relating to this conduction. One is, what is conductivity? Thermal conductivity, K. So, K we can define like this, that Q by T is equal to K when A equal to 1 meter square and what do you call theta 1 minus theta 2 by x is equal to 1 Kelvin per meter. So if these two are like this, then rate of flow is numerically equal to the conductivity of the material. So we can define the thermal conductivity of the material is numerically equal to the rate of flow of heat through a section of the conductor having unit area of cross section maintained at unit temperature gradient. This is how we are defining the thermal conductivity. Okay? Now what is its unit? That's another thing. If you want to write the unit of this one, then we will be taking the equation straight away for K. You can write K equal to, from this one, K equal to Q by T into A into theta 1 minus theta 2 by x. This is the way we can write this one. And when I write the unit for this one, heat energy joules divided by time second, area meter square, then temperature difference Kelvin divided by meter. So meter and 1 meter from this goes joules per second, meter and Kelvin in the denominator, and you will be getting joules per second. Together I can take it as watt per meter per Kelvin. So this is the SI unit of conductivity of the material. Alright? Okay. Now one more point from this one is that suppose I take this particular equation. This particular equation says that k into a into theta 1 minus theta 2 by x. This is coming here. When I rewrite this, or when I rearrange the writing, like q by t equal to theta 1 minus theta 2 divided by x by k into a. We can write it like this, x by k into a. Then it says that rate of flow of heat, heat energy flowing per time, it is purely depending on what you call the temperature difference. If this temperature difference is 0, rate of flow is 0. Then you can treat this one as a quantity called x by k into a can be assumed as thermal resistance of the material. Thermal resistance of the material, because temperature difference by thermal resistance is equal to rate of flow of heat. You can compare with this one with what you call current, that is charge divided by time. Charge divided by time, that is electric current I, which is equal to potential difference divided by resistance. This is according to Ohm's law. So this is electric current is equal to potential difference by resistance. This is electrical resistance. Then here I can compare the same, that rate of flow of heat, we call it as heat current, is due to temperature difference divided by thermal resistance. Okay, so these are the basic points relating to conduction, and this equation can be written only when the steady state is reached.